So in today's class, I'm going to introduce you to ADC and DAC designs. A little bit, not at the transistor level, but at the gate level. So ADC stands for analog to digital converters, and DAC stands for digital to analog converters. Okay, because all our CPUs and mobiles and most of them, they work on the microprocessors. Everything work in the digital domain, but all signals in the actual world is all analog, right? And the color, what we see, what we smell, what we the temperature, what we feel, what we the voice, what we hear, everything is analog. So ultimately the analog signal requires to be captured, made it to digital, and then you do whatever is the processing with it, transmission, reception, and finally that digital signal needs to be again converted to analog for the human beings, like so you have, so that is the so ADC and DAC becomes an important modules. Okay, so if you see here, this is the simplest way of converting and analog signal to digital. Okay, these are all known as comparators. So they will give an output signal 1 if the voltage level available at the plus terminal is greater than the what is available in the minus terminal. Okay, so these are all these are all known as comparators. Now I have a reference voltage out here, right? And I have R. So okay, 1, 2, 3, 4, 5, 6, 7 resistances which are connected here. So I have 1, 2, 3, 4, 5, 6, 7 comparators also out here. So what will be the voltage which will be there on out here? It will be, right? So since there are so many 1, 2, 3, 4, 5, 6, 7, 8 resistance in fact. So the voltage available here will be V divided by 8. Right, so this we know from our electrical sciences, right? If you this is total 7 resistance, this is only 1 resistance, so V into that 1 resistance divided by the total resistance, which is 8R, no, so potential divider rule. Okay, we use the simple potential divider. So the voltage which will be available here will be V divided by 8. Here it will be 2V divided by 8, or I can write V divided by 4. This will be 3V divided by 8, or 4V divided by 8, 5 divided by. So as you keep moving up the comparator, the voltages available in the negative terminal is higher. Okay, so now I give an input signal. So suppose the input signal is initially 0, right? So you will find all the outputs from the comparators will be 0, because you have on the plus terminal you have zeros, whereas on the positive terminal you have certain voltages available. So it will be all zeros. Now as the input signal keeps increasing slowly, if it crosses V by 8, this comparator output will be 1. So you will have an output 0, 0, 0, 0 here, 1. Right, and further the input signal goes further high, then the output from the second inverter also will go high, because this will also remain high, this will also remain high, so both will be high, right? If the signal is suppose V by more than V by 4, so it is more than V by 8, so this will also be 1, this will also be 1, and further the signal goes high, again this will become 1. Right, so this is known as a thermometer output, right? So it is not like this is 0, then and this becomes 1, then this becomes 1, this becomes 0. That doesn't happen. It is all zeros, then this will become 1. In the next case, both will be 1, and then the signal increases. All 3 of them will be 1. Then the fourth one also will go 1, like that. So I have some kind of digital output. Now there are 1, 2, 3, 4, 5, 6, and 7 and 0, 0. So there are so many different conditions, 8 different conditions, all zeros, or just one here, then 2 ones here, 3 ones here, 4 ones here, 5 ones here, 6 ones here, 7 ones here. So 8 different conditions are available here depending on the input voltage, and those 8 conditions you just require a 3-bit line, right, to encode it, right? 0, 0, 0 will can, so you can make an encoder logic, normally a priority encoder like this, right, will be good enough. This is an if you remember priority encoder, we studied a few days back, in which if D0 is 1, it will be 0 0, and if D1 is 1, irrespective of what is there in D0, it will be 0 1. So we saw a priority encoder, right? So you can use a kind of priority encoder also, or you can design your own encoders, right? So these are all digital inputs available out here. So this is the analog input. These are the digital inputs. These digital inputs are thermometer type. Like the first case, it will be all zeros, then 1 all zeros, then 2 ones all zeros. So you have so you can have you can encode that into an 3-bit data. Okay, so this is how an analog to digital converter works like. Okay, now you could have here, if you see here, the hardware requirement is very high. You require 1 2 3 4 5 6 7 comparators and an encoding logic. So this is purely a combinational design. Here we are going for a sequential design. So in the sequential design, what we are doing out here is, see, this is an counter. Okay, so the output of a counter is the digital data which we require. Okay, so this digital data output is corresponding to the digital value corresponding to the input analog. Suppose this now I am using an in the ADC I am using a DAC block also. We'll study how this DAC block works in the subsequent slides. So time being, just understand this is a block which converts the digital data into input. Okay, suppose let me take an example. Suppose the input voltage is 5. Okay, so if this digital data is also corresponding to 5, so this DAC will also convert that digital into analog, and I will have 5. So both these input voltages are the same. So the control logic will say, okay, counter, you don't do anything, you can remain where you are, and it will not generate the clock signal. Okay, suppose I am giving input 5 volts and the digital output, the output of the counter is corresponding, this is a digital output, remember that it is corresponding to 4.5 volt. Okay, so this DAC will generate a 4.5 volt here. So now I am giving 5 volt here, I am giving 4.5 volt here. So this comparator will give a high signal to the control signal, telling, okay, so I need to increase the count. Okay, so this will trigger the clock and it will give the counter signal, up count signal. Okay, we have seen in the counter design also how we can have an up down counter, right? So this will be up signal, so the counter will start counting up. So when it reaches this digital count reaches corresponding to 5 volt, then I have 5 volt here, and this control logic will stop the counter. Okay, in case suppose similarly, if this counter, this is this count available here, I am giving 5 here and the count is say 5.5 volt. In that case I will have 5.5 volt here. So this will tell the control logic I have to reduce the count. So this will give an down count command here. Okay, and the clock will be triggered. So this counter will start counting below. Okay, so whatever is the contents of the counter will start reducing till the digital output correspond, like from 5.5 it will start counting down and it will reach to 5 volt, where then it will stop the count. So is this block diagram understood? Yeah, Sachin, Kishan, is it okay? So the working principle is simple. Only thing is we are using a sequential circuit out here. Okay, yeah. So now if you see here, what block we were missing out here is, like if you see here, there is an input signal. When this computation is happening, right, so you can't have the input keep changing, right? So it has to, the input has to remain stable till this count, otherwise what will happen, continuously this data will keep changing if the input is fluctuating here. So you can't have that. So you have to give time for this counter and the DAC to settle out here. So that is the reason we use a sample and hold circuit. Okay, what it does is, if we have an input signal here, so we sample it and we hold that value till this finishes the computation. Okay, so you have something known as sample and hold in all A to D converters. The first block will be an sample and hold block. Okay, so now if you see here, this is the so I was mentioning, so if this is the analog signal, so I am going to sample it at regular intervals, and I am going to keep it on a constant, so that the ADC can do the process, convert it into analog and digital signal. So this becomes now the input to the ADC, right? So I am doing a sample, so I am not allowing this input signal to the ADC continuously changing. I will just sample it at regular intervals, and I will keep the signal constant, so that allowing the ADC to compute. Okay, so here there is an criteria which is known as Nyquist criteria, which says that if you sample this frequency, this analog signal at a frequency which is twice that of the maximum frequency available in this signal. Okay, so this signal, suppose this is a voice signal, I can have this variable frequencies in this, right, from 0 to 3 kilohertz. Then if I sample it at 6 kilohertz, then I will be able to reconstruct this signal even with these samples. Okay, I don't have to transmit the entire signal here, right? Even if I transmit some samples, I will be able to reconstruct the signal at the receiving end. Okay, provided the sampling frequency is twice that of the maximum frequency of this signal. So that is known as Nyquist criteria. So that is not an issue. So only thing which we need to be careful is that when we are sampling signals, so we can sample it at a frequency at least twice that of an input signal. You don't have to continuously transmit the entire signal. So this sample and whole thing will work fine. Okay, with so that is what this says. Okay, now these are some things which we need to know. One is the resolution. These are some of the figure of merit of analog to digital converters. If you see this, if this is the total analog range, okay, from 0 to 10 volts. Okay, if this is the range, okay, which I call it as VH minus VL. VH is 10 here in this particular case, and VL is 0, so 0 to 10 volt. So this is the range, and if I am using an 3-bit encoder, then I can have maximum number of 8 levels, right? So so the resolution becomes 10 minus 8 1.25. Obviously the resolution is big, that means it is not that good. Okay, it cannot distinguish between two analog signals which are less than 1.25 difference. Like for all voltages between 0 to 1.5, right, and it will read it as 0. Any voltage between 1.25 to 2.5, it will read it as 1. So you see, this is a huge step. Okay, so now if I want to increase the resolution, in that case I have to increase the value of n. Like if I use an 16-bit ADC, right, then if you see, there become very small steps, right? So if you see, the resolution now becomes 10 divided by 2 to the power of 16, that is 0.000015. So you see, it is now very fine resolution. So if you increase n, then the resolution will be better. Obviously the hardware requirement and things will also increase. So depending on what is your requirement, you will fix the value of n. So it is not that you use a very high n and there will be no penalty. Okay, if you use very high n, obviously the resolution will be fine, but the total power requirement and the hardware also goes up accordingly. So you have to judiciously decide what should be the value of n. Okay, so this is about resolution. And also there is something known as quantization error. Okay, now suppose for an input signal from 0 to 1, I am taking this digital output, right, and from 1 to this step I am taking this digital output, right? So if you see here, when the input analog signal is here 0 0 0 out here, so there is no error, right? Okay, but as the signal keeps analog signal, this, the blue line shows the analog signal, as the analog signal is increasing out here, right, the error increases. The error increases. Okay, the keeps error. So when it reaches here, it will be the maximum error. Again here it is making an step change out here, so the error will come to 0 out here. Okay, again the error will keep increasing here, right? At this point the error is 0. So you will find if I plot the error, it will be something like this, and the max error will be the equivalent to that of 1 LSB. Okay, so this is known as quantization error, right? But if you try to make an ADC graph like this, wherein if this is the step size and I'm making a decision here, if the in between these two, right, here, like if the signal is beyond this level, it will make a transition. So again, so if you see here, here is 0 error. Till here it makes a positive error, and here it is making a transition at this place itself. So now again this will be 0 error, and then the error will again start. For here it is the negative error, right? So you have equally distributed. If you have this reference line out here, the error will be equally distributed between the positive and negative LSB. Okay, whereas the max, although the total error out here is from minus 0.5 to plus minus 0.5 LSB to plus 0.0 LSB, but the maximum error is 0.5 LSB. So this has got some little bit of an advantage. Okay, so this is how an A to D converter quantization error looks like. And now again the quantization error also will decrease with the n. So if you keep increasing the value of n, okay, so the total net quantization error decreases. Like in the case of resolution, same is true for quantization also. If you keep increasing the value of n, that means if you are having an instead of an 3-bit ADC, if you have an 8-bit ADC, though it will significantly reduce the quantization error. Okay, so again the penalty will be increased hardware out here also. Now there are a few other figures of merit. Okay, one is known as differential non-linearity. Okay, what it is, suppose this is an ideal line for an ADC. Okay, if I join the mid values of these step size. Okay, but in a practical ADC you will find if like here in this case, okay, it is an ideal case. If I draw a line which is connecting the midpoints out here, so you will get a straight line like this. Here also, if I am connecting the midpoints of all these steps, right, now here also if I connect all the midpoints for an ideal ADC, the dotted line will be the dotted line. Whereas an practical ADC, okay, these step size, if you see here, they are not uniform. Okay, why? Because if I go back to these circuits here and all, also, so for example, for a flash ADC, all these amplifiers, they don't they are not linear for the entire range of input analog domain, right? So suppose this is supposed to compare from 0.25 right, V by 8 and V by 4, right, exact at those values, and for the so these the same are being used, right? Like this is supposed to detect 7 by 8 V, this is 6 by V, 6 by 8 V, right, 5 by 8 V, but in practical op amps, okay, there will be small variations. Okay, you can't have it is not a digital thing. There's an analog blocks also in between, so that results in some non-linearity here also. So if you see here, this step size here it is it all should be ideally should be 1 LSB, but here you will find it is 1.5 LSB. So I call the differential non-linearity is here is 0.5 LSB, okay, plus 0.5 LSB. In some cases you will find that here the step size is on the horizontal axis. If you see here, it is only 0.5 LSB, whereas it should be 1 LSB. Okay, this step should ideally change at every 1 LSB. So that is not happening out here. So you will say the differential non-linearity here is minus 0.5 LSB, right? So that is what an DNL is all about, right? So this is DNL comes from the analog components which are there in ADC, which are not linear for the entire range of operation. So this is what DNL stands for, right? And similarly, there is something known as integral non-linearity. This is the ideal ADC curve. The actual ADC curve is this. So if I connect all the midpoint, so I'll get this curved line, and wherever the max difference between the ideal and the deviated line and the actual line is known as integral non-linearity. Okay, so ideally this should be 0. Okay, so if it is more, that means okay, your ADC is not that good. So these are some of the figure of merits which we use to compare several ADC designs. Okay, so you should have some figure of merits, right? Like if you have a car, you say the mileage and comfort and different figures of merit. Similarly for ADC, resolution, accuracy, ideal, right, DNL, INL, these are all known as the figure of merits. Okay, so when you compare two ADCs, you will compare all these figure of merits. Okay, so this is INL. And accuracy is actually sum total of all the quantization errors and all. So how faithful is the output with respect to the input. Okay, so that defines the accuracy. Okay, that defines the accuracy, right? So all these errors will finally result in inaccuracies, right? So accuracy is only sum total of all the errors. It defines how, if I say it is accurate 0.001%, that means the output and the input can differ only by 0.001%. If I say the accuracy is only 10%, that means the output can differ the input by 10%. So that is bad, right? So the accuracy is generally defined in terms of percentage of the input, and it should be if you like we say the maximum error permitted will be 0.001% of the input. Okay, so that means it is a good so that kind of definitions are there for accuracy. Okay, now let's see one more topology for analog to digital conversion. You have a sample and hold circuit. You have an comparator. Suppose the input voltage range is 0 to 10 volts. Let me take just one example. Okay, so I give V references 10 volt in that case. Okay, suppose if it is 0 to 20 volt reference, then it is the input voltage, then I will give here as 20. Suppose this you can say V reference indicates the maximum input voltage, so I give V reference out here as 10 volts out here. Okay, now if you see here, let me go to the what it does is, let me take this, right? So initially this successive approximation ADC, okay, feeds and data of 100. This is an 4-bit successive approximation ADC. You could have 5-bit, 6-bit, 7-bit, whatever. So we will try and understand how an 4-bit and SA ADC works like. Okay, so initially I am going to feed 1000. Since V reference is 10, right? So since it is 1000, the output will be 5 volt. Now how is it 5 volt? If you see reference voltage is 10 volt, right? And 4-bit can have 16 different levels, right? 16 different levels, right? 2 to the power of 4. So each level will be corresponding to 0.625, right? 10 divided by 16. So if I am giving 1000, this is 8th level, right? So 8 into 0.625 is 5. So this is somewhere on a halfway through, right? 0, then it starts again 001. So 100 is exactly in the halfway through. So if I give 10 here, I will get a 5 here. Now it is going to compare with the sample and hold signal which is here. Suppose the input is 5.2 volt, for example. If it is so it will give an since the input is higher, it will give a 1 here, right? So what it does is it will shift. If the input signal is 1, that means the input signal is high, it will retain this 1 and it will push a 1 here to the next bit. Okay, if it is 0, right, if this signal which is coming from the DAC is less than the input signal, in that case this will be 0 and next will become 1. Okay, that is the logic which will be followed. So if you do that, since this is an 4-bit ADC, in 4 cycles you will get the desired results. So we'll see an example. Okay, so the logic which requires to be followed is to be understood. Okay, first you start with the midway point, okay, which is 1 0 0 0, right, and you compare the signal. If the input signal is higher, then next bit I will make it 1, and if the input is lower, then also I'll make the next bit higher, but this bit I will make it 0. Okay, so if I go to the next slide, things will be very clear. Suppose it is 1 1 0 0 0, right? Now I am which is corresponding to 5 volt. I am comparing it with 5.2 volt here, right? So for 5.2 volt, that means the input is higher, so it will go to this state. That is, the next also has become 1. This is also remained as 1. So 1 0 0 0. And what is this voltage corresponding to? Okay, if you see here. This is digital to analog, right? So I have 1100 now. What is the corresponding analog voltage? We saw that 1100 is what? 8 plus 4, 12. 12 into 0.625, it is 7.5. So this is 7.5. And now now here I have got 7.5. Now the comparator will tell, okay, now I have to reduce the voltage because input voltage is only 5.2, right? So from here to here, now if you see here, this one is converted. This one will be retained here because that was the first cycle. This one, the second one, has become 0 and it has become a 1 here, right? In this case, what has happened? 5.2, the input voltage was higher, so that is why this was retained as 1 and this became 1. Now, whereas in the second state, okay, it is this is 7.5, whereas the input voltage is lesser, so that is why this has become 0 and this has become 1 here. Again, I am comparing in the next cycle. In the next cycle, again it is this is 6.25, whereas my input voltage is only 5.2. So again, this will also become 0 and this will become 1 out here, right? Again, this will again be compared in the next cycle. Then again you will find it is 5.2, this is 5.6, so this will also become 0. So my final answer will be 1000. So this will become 5 volt. Okay, so you can try it out for this particular chart for different voltage also, and you can expect this kind of numerical in your exam also, where I will specify what is the input voltage and you might have to draw this kind of chart. Okay, so if you see here, the final answer is 5 volt and not 5.2. Why? Because if you see here, I am using an 4-bit ADC and the maximum resolution is 0.625, right? So obviously the first level will be 5 and the second level will be 5.625. So 5.2 is nothing. It is in between two levels, and that is the reason it is this final answer will be 5 and not 5.625. Okay, so you can't have 5.2 here because the resolution itself is only 4-bit. Okay, so this is how an successive ADC works. Okay, so similarly, now coming to digital to analog converters. So we have seen 2 or 3 topologies of how ADC works, right? So first we saw this is known as a flash ADC. Okay, this is known as a sequential ADC, and then we came here. The third kind of ADC was successive approximation ADCs. So 3 kinds of ADCs we learned till now. So let's see how an DAC work. This is a digital to analog converters, right? Now you have, suppose you have 3 digital inputs. Okay, so that means if it is 0, V1 will be high, and if it is 1, V1 will be 0. So these are the 3 digital inputs available here, and also I am assuming that this RL is much greater than R1, R2, R, and obviously if it is much greater than R, it will be greater than R by 2 and R by 4. So so we don't consider this RL in the derivation here. Right now, suppose this is what VA is the sum total of these three voltages which will be applied here depending on the resistances which are put here, right? So I can use superposition theorem to find out what is the output voltage based on these three input voltages. So let me try and use the superposition theorem, which you might have done it in your electrical case. So first let me find out what will be the output voltage because of V1. So for that I'll ground V3 and V2. If I ground V3 and V2 and just consider V1 voltage and try to find because of V1 what will be the voltage at VA, right? So if I so RL is also not there because it is very high. So these two will be grounded, like in superposition theorem you might have learnt in your electrical classes. Okay, so you take one source at a time and the other voltage sources will be grounded, right? So we ground these two sources, so you will become R4 and R2 will become parallel in that case. So I have that parallel resistance formula, R4 R divided by 4 and R divided by 2 multiplied by R by 4 plus R by 2, so I'll get R by 6, right? So this becomes one resistance. And now what is the voltage VA? Again I use the this is ground out here, so and this total resistance is R by 6. So I have the potentiometer rule, right? Voltage divider rule to find out VA, right? What is the voltage divider rule? It will be V1 into this resistance, which is R by 6 divided by R plus R by 6, right? So I get V1 by 7. So this is the output voltage because of V1, right? Similarly, if I have to find out what is the voltage because of V2, okay, what do I do? I ground V1 and V3. So I have R and R by 4 now parallel. So R and R by 4, if I take a parallel of that, I will get R by 5. And again for V2 into I take then voltage division rule. So I get R by 5 divided by R by 5 plus R by 2, this R by 2. So I get 2 V2 by 7. If I do the same thing for the third source, I will get the parallel resistance R2 and R. If I take, I will get R by 3, right? And then if I use the potentiometer rule, I will get 4 V by 3. So if I do the sum total out here, so it will come as 4 V3 plus 2 V2 plus V1 divided by 7. Okay, so if I say if I take all V1, V2, V3 to be 1 volts, okay, so if for a digital input of 0, 0, 0, so I'll get a 0 volt, 0, 0, 1. If I give 0, 0, 1, right, and 1 corresponds to 1 volt, suppose if 1 corresponds, if I give 0, this is a digital input, so I give 0, 0, 1 out here, so I will get suppose 1 corresponds to 7 volt, okay, just for simplification. So if 1 corresponds to 7, so I will get 7 by 7 as 1 volt, okay. Now if I have suppose 0, 1, 0, right, so this will and 1 correspond to 7 volts, so it will become 2 into 7, these are 0, so I'll get a 2 volt output, right? So similarly, if I have V3 as 7 volts, which is corresponding to digital 1, and these two zeros, so it will become 4 into 7 divided by 7, so I get a 4 volt. So you see, depending on the digital output, I will get a corresponding analog signal out here, analog value, right? So for all 8 combinations, I will have an 8 voltage. It is like from binary to decimal conversion. Okay, so this exactly does that. You have an binary input. Okay, each of them you are having that weightage out here. So binary to decimal conversion is nothing but digital to analog conversion. So this circuit exactly does that. Okay, so this is how an DAC works like. Now you could also have a network like this which does the same function. Now if you suppose I have to see what V4, how much is the voltage V4 contributes towards the output. So I will ground V1, V2 and V3. So if I ground that, then R2, these two resistances will become in parallel, so that will become R. R and R will become in series, that will again become 2R. 2R and R will become in parallel, so that will become R again, and R again in series will become 2R. So that is why this is known as R2R ladder. Okay, so that 2R will become R, and then R and R will again become 2R. So ultimately you will have 2R here and 2R here and ground. So VA will be V4 divided by 2. Okay, so I can write it as V4 into 2 to the power of 3 divided by 2 to the power of 4. So 1, so the 1 and 2 remains in the denominator, so it will become V4 divided by 2. So if I do the analysis for the rest of the signals also, so I'll get V3 into 2 to the power of 2, V2 into 2 to the power of 1, so V1 into 2 to the power of 0 here. So again this is like binary to decimal conversion. So the net voltage out here will be kind of analog signal corresponding to the binary bits. Okay, so this will be the LSB here, and this will be the MSB here, right? So in the previous case, this was the LSB and this was the MSB out here. In this case, this will be the MSB, this will be the LSB. So you have to be careful where you put the MSB and LSB. Okay, practical circuits, we generally have an op amp. This is a unity gain op amp, and you have these R2R ladders, and there will be a reference signal, and if you see here, these are the switches which will be operated by the digital signal, right? So if it is 0 0 0 0, if the 4 bits are 0, you will find all these switches will be here connected to the ground, so you will have an 0 output, right? If only the LSB is high, so this switch will be put here, so you have V reference going out here, so correspondingly the output voltage will increase. And if the MSB is switched on out here based on the digital input, so you have V reference going out here, so correspondingly the voltage will be still higher. So this is the practical circuit using an R2R ladder and an unity gain op amp. Okay, so you may not have studied op amp till now, but probably you will learn it in your next semester. But just for the sake of it, you don't have to remember this particular circuit as of now, because you have not yet done op amp theory. Okay. So even digital to analog converters also have these figures of merit, resolution. Okay, so like if I have an 8-bit D to A converter, it can have a total 256 different levels, different values, and 256 minus 1, 255 levels. Okay, brackets you can have 255. So if the total range is the percentage, okay, will be 1 divided by 255. So 0.39% is the resolution percentage. Okay, so if it is 10 volt, then 0.39 39 volts, 3.9 volt will be the resolution. If it is 100 volts, then 39 volt will be the resolution between two bits. Okay, so so that is how this is the these many different for 100 lines. Okay, sorry, this already 100 is catered for. If it is 100 volts, then 0.39 will be the difference between two levels. Okay, so this is how the percentage resolution is calculated. So the formula would be 1 divided by 2 to the power of n minus 1. Okay, this n has to be prefixed out, 2 to the power of n minus 1 into 100. So that is the resolution, percentage resolution. Okay, the formula for percentage resolution, 1 divided by 2 to the power of n minus 1, right? Here, like 1 divided by 2 to the power of 8 is 256, so I take 255 into 100, so I got this value. For general value of n, this is 2 to the power of n minus 1 into 100. So this is the resolution of what we have, digital to analog converters, right? So these are some of the more errors which are sometimes seen in a practical digital to analog converters. Like as the digital input keeps increasing, the analog output has to increase linearly, but sometimes you will find this is not linear. The slope is higher than 1. Okay, the slope has to be 1 actually. The slope is this known as the gain error, right? Similarly, you could have an offset error also, like when the input is 0, like the analog output is more than 0. Similarly, corresponding, so this offset error with respect to 0 continues. So this is known as offset error. So accuracy is again sum total of all the errors which we see here. So generally, when you see the specifications of D2A converters, so accuracy will be specified, okay, in terms of full scale error or zero scale error. So all these errors will be given in the catalog of an ADC. So and there will be the certain other figure of merits also or D2A converters. One is known as the conversion speed, or it's known also settling time. That means once a digital input is given, okay, this is going to take some time for the analog to get settled at the output. Okay, this is also there for an A to D also. Okay, this is common to both to DAC and ADC. Conversion speed, okay, conversion speed is once you for an analog to digital conversion, once you sample the signal, okay, for the final digital signal to get stabilized, it will take some time. For a D2A signal, once you have placed the digital input, it will take some definite time for the analog signal to be stable, to come to a value which is corresponding to the digital input. Okay, so that is known as the settling time. Okay, so your clock frequency has to be has to cater for that settling time. You can't keep giving a digital input okay, in which the time period is less than the settling time, right? Then the output will not follow the digital signal properly. So for this these converters to work properly, you have to cater for a clock speed, and the clock time period has to be greater than the settling time for the ADC or the DAC to finish the computation and give the final output, okay, corresponding to the input. So that is known as the settling time. So some of these ADCs, it has got up to 5 nanosecond delay. So you can understand, you cannot operate this particular in gigahertz. So it has to be, because gigahertz corresponds to 1 gigahertz corresponds to 1 nanosecond. So at least 5 nanoseconds is the time. So no, you have to have at least 1 giga by 5, that is a 200 megahertz. So that kind of frequency only, clock frequency only you can use for this particular ADC. So when you are picking up an ADC for a specific application, you have to see this figure of merits which are specified in the catalog, and then only take a final call of which ADC you need to use for a specific purpose. Okay, so thanks a lot now for today's